we get experimental. SciAnts. We're curious, non-judgmental.
Bees and social wasps and how they build, like what their architecture looks like when inside of their nest. Like, what do the combs look like? How do they make the combs? What is the shape of it? So the title of this paper, again, honeybees and social wasps reach convergent architectural solutions to nest building problems. So the idea is that these two animals make nests and they independently came to the exact same solution on nest building. I guess not even by coincidence, they just did. And it's, again, they talked about in the abstract that these hexagonal shapes built by honeybees and social wasps are an example of adaptive architecture. Hexagons minimize material use and the importance of this hexagonal shape that's repetitive in nature, right? This hexagon building evolved independently in bees and wasps, but in some species of both groups, the hexagonal shapes are dimorphic. So small worker cells and large reproductive cells. So this is the conundrum, right? If you're making a hexagon, it's one thing if every hexagon is the exact same size, right? Because they'll just keep going and there's no gaps, right? But here, there would have to be gaps if you're making all hexagons. If you're making a little one and a big one with respect to, who's inside of it. So the reproductive one would have a large hexagon full, the worker one would have a small hexagon full. And so it's hard to know, right, how they would make up for that in terms of what they're building. So they're, saying that workers would have to build the hexagons together in a different way. And so they were looking at 5 bee species in this study and 5 wasp species. And they looked at over almost 23,000 cells that were built and trying to figure out, like, what exactly do they do in terms of the architecture to account for these differences? So yeah, they were trying to look at what the solution was for this honeycomb issue. So, and just to give you all an image, here is the problem that they face. So there is this species, this M. mesoamerica. All the cells are the same size. Nest with the wasps, are they badly misshapen to the different size of the hexagons? Like the overall, so Trey, it seems like there are some wasps and some bees that have this difference in size for workers and the reproductive. And so Trey, this species doesn't have this difference in size. And so you're seeing this regularly repeating hexagonal pattern. But then there are ones, Trey, like you were saying, that maybe the nest size, could be different because of the hexagonal shape. And so they're leading us in this paper with the problem figures, right? So there's these species here. The worker cell and the reproductive cell are very different sizes, right? And so the idea is if they're so different sizes, they cannot be repeating like this. And you're going to have gaps here where this has a lot more material than this region here. And so it's lack of efficiency. And how do they get around wasting resources? So does that potentially compromise the structure or no? So one might surmise that they would, but what they end up doing, Trey, this is the important thing. The way they actually counteract that, so the researchers were saying in the paper it could compromise the structure, where you could have a real mess up in terms of what the connection is for these particular shapes. But it turns out, so they looked at 8 different species of bees, 8 different species of wasps, and they found that this hexagon rule isn't actually a rule. Yes, there's a completely new geometrical shape. Yeah. So what's wild about this is where they're like, everybody does hexagons, and it's always a hexagon. But it turns out it counted and measured 23,000 combs. And what you end up getting is pentagons and heptagons regularly. And so this is that transition period between the bigger cell and the smaller cell. You get this extra side to keep that structural integrity and to minimize being wasteful in your resources. This is the actual important figure here. They led with a problem figure. They did say, Trey, that there were regions, within the nest where there are gonna be issues. That's an extra layer of complexity. It turns out these workers, when they hatch, are not as good at building these combs as they are as they age. So it seems like part of it is innate. They have an innate behavior of building these combs, but as they get better, or if they watch experienced individuals build, they themselves are better. And so they did notice in the study, they were like, there are instances where you get this here. You see there's a huge gap right here, and it's a lot of excess material. And they were finding that was with young hives, or hives, they painted newly hatched workers, and then they saw where the newly hatched workers were working. They weren't doing these adaptations, these extra shapes to have those two together. Rose says, reach a conclusion if these shapes are based on an objective, the type of bee, or it's a massive architecture understanding a nest. So it doesn't look like it's on a type of bee. So it looks like bees and wasps do this. Independent of the species, it's dependent on if there are size disparities between different castes. So if there are reproductives and workers that are different sizes, they're going to be making these new geographical shapes. And it presumably does mean there's some kind of connection to the nest architecture overall, but they weren't able to truly measure that. They're also used for the brood. There are embryos that develop in there as well, not just keeping honey. So they're used for everything for it. They've adapted to different sizes by creating new shapes. It's wild to me that there is this layer of complexity. And it shouldn't be wild, right? Because it makes sense. Like, you and I learn better after we've done a task. It's just when you see a behavior that's innate, like they know it from the beginning, but then it's also plastic in that they can learn and get better. I think it makes it all the more fascinating, right? Of like that level of complexity. It's like, well, this is a really complicated animal. I wonder how they're learning that additional feature of it. And so that much complexity, they didn't go into the neuroscience side of things, but it was still like a really cool, like nonetheless feature of it, right? So they're mixing in these 5-sided and 7-sided cells. Again, after looking at like almost 23,000 cells, it happened a lot more often, and it's alternating cells, and it allows for there to be different sizes of the 6-sided hexagon, and they still fill them too, which is really neat. So the study, and they were saying, it's really interesting that there is this like difference in the hexagonal size of these, and they did say, the reason it was surprising was because hexagons have been known to be the most stable shape. So in terms of being compromised architecturally, that was surprising that they found this, and yeah, it was really super cool. Actually, some that are still not known of like what the direction is of in this building component of it, but there definitely is this element now where the bees intentionally will build, like it seems there's so much more intention, right? Like if they're building these hexagon shapes at different sizes, they're then building pentagons and heptagons within there to make up for these size differences. Like that shows a higher level of complexity than just building the same shape over and over and over again. Bees who build other shapes didn't do so well failed. Oh, if there was evolutionary selection pressure for it. Maybe, Chris. That's a really cool question, Kale. I'm not sure like what influence the shape, that hexagonal shape, has on the dancing behavior, but I don't think it's wild to think that there is an influence of it. There you go. There we have both the pentagons and the heptagons. So they figured out, again, that they analyzed all these like absurd number of the pictures of the nest made by many species of honeybee, wasp, yellow jacket, and a species of paper wasp. They developed a automated image analysis tool. Yeah, so they did they had a roboticist on the paper who developed this image algorithm to do like all the shapes and sizes of the shapes and all that, so they could do it all automated, which is really, really cool. So they could do it to like 23,000 cells, to cell walls, how many neighbor each cell has, and apparently they had to double check by hand to make sure that the automation works. So they had a bunch of undergrads do the checking as well. And so yeah, apparently, Rose, I thought this was kind of neat that if you look back at the data, like the past data sets, looking at anything that's similar in this vein, researchers ignored those cells that looked funny with the idea of it like this is an error on part of the bees, or it's misshapen because of how we're looking in the nest, or something like that. And with this mathematical model, they're like, no, that doesn't seem to be the thing. This is far too common. This is not an accident. This is clearly like an intentionally built, oddly shaped cell, which I think is really, really cool. And the reason they suspect that it's the 5 and the 7 is because the 5-7 has the same number of open sides as a pair of hexagons, which is 10 open sides. So it doesn't mess up the pattern. So you're having the larger size of a 7 side allows for the bees and the wasps and paper wasps to make larger hexagons on either side of it. So they're always building, they said they build the 5-sided one first, and then they build a 7-sided one, and then they can build a large 6-sided one to connect to it, which again I think is a really, really cool like component of the geometry and the mathematics, and like when this exactly like happens on there. Yeah, exactly. Skew the data, Chris, when they didn't include these numbers, but when they actually did it, it's like, oh, this is actually a thing. And yeah, they find that they are wondering like when this evolved. Common ancestor of bees and wasps has been gone for like 180 million years ago, so they're not really close in terms of relatedness anymore. They also build out of different materials, but they do this behavior. And so the question is, right, did this evolve independently and those two separate branches, or did the common ancestor already have it? And that is something we might never know. But I thought this was a really freaking cool paper, chat, about this like architectural nest building and how they went about it. And again, like the machine learning to like optimize, right, like how they did it, like the mathematics behind it and the machine learning, and just, it was really cool.